Welcome back to Manish Kumar channel. So today we are going to discuss about the problems on continuity. Now let me discuss a very important problem, right, on continuity. So fz is equal to log of z, right, this function. So this is a very important problem and it has a very strong connection with continuity and differentiability and many more, even antiderivative. So a lot of stuff is very well connected with logarithmic function. And you have seen my previous video where we have discussed about this function. This function is a multi-valued, right? And then we have to be very careful while defining such type of functions because in complex analysis, anything can be analyzed for single valued function. So for a multiple valued function, we have to be very careful. Okay. So now let me just explore some about the continuity of this problem, whether this problem is continuous or not, right? So now we can discuss about the continuity of this function. Okay. So this can be written as ln mod z plus I into argument of z, right? That can also be written as ln r plus I theta plus 2n pi, where n belongs to z, right? So it means that if you see my previous video, you will find out that modulus z means what? If z is r e power I theta, right? So modulus z is nothing but your you can get it like modulus of r, and I theta is 1. So basically r positive, right? Greater than 0. And this function is, I'm going to talk about z defined on c minus singleton 0 point we have removed from the plane because log 0 is not defined. Okay. So now if you look at the structure in xy plane, right? And if I say r, right, distance, and then theta is an angle, right? Then you can find it out like circle, and then again circle, and then again circle, and then you can get multiple circles, and then you can find out this r or this r or this r. So for multiple theta, you will get this line for r and circle for theta, right? So when you transform into the z uv plane, right, this is z plane, and when we say w plane, right, so function your fz equal to log of z. So in that case, if you have u and if you have v, right, v, so what had happened here is for theta, if I'm saying like this, let's say uh, theta equal to 0 and theta equal to this, because this r ln r ln r will be the u and argument of z will be your v, right? So what had happened here is ln r will be the perpendicular line, right? This is ln r. Okay, so this is going to be your ln r, right? So you will find the parallel lines, right? And for theta, how much rotation you are going to get it, then you are going to get multiple parallel lines, right? So these all are the multiple parallel lines we are going to get it. Okay, so now the question here is if I see this sheet, for example, if this sheet is let's say minus pi to pi, right? And in this seat, let's say this gap is 2 pi. So this seat is pi to 3 pi, right? Similarly, you can see the other seat of 2 pi. So in this seat, these are the sheets. So what had happened here is, if you see for this function, if I'm going to say that fc, right, is going to be ln r plus I theta. So ln r plus I theta when n equal to 0, right? When n equal to 0, you will get theta, right? And that is going to be my principal branch. You know, in principal branch, what we are assuming that theta lies between minus pi to pi, right? This is my principal branch. So in principal branch, what had happened here is the function has some value, right? Minus pi to pi, and these all are the branch line, right? At minus pi, at pi, all are the branch line, right? Where function has multiple valued. So in each sheet, this is called Riemann sheet, function has unique value, right? Not multiple valued. But in each theta, if you increase theta here and there, so in different sheet, the function will change because of the fact that if your theta is in principal argument, this is your principal argument, right? So in principal argument, if I say my theta will be in range minus pi to pi open, right? So this will be a unique value. Now if I say theta from, if I say pi to 3 pi, right? So what had happened here is, in this range, you are going to get n equal to, if I plug n equal to 1, what am I going to get? Ln r plus I theta plus 2 pi I, right? N equal to, for n equal to 1. Okay, one rotation. So here no rotation, one rotation, right? Two rotation, three rotation, like that. So if you see these two functions, this function has jump discontinuity, right? Jump is, how do you calculate jump? This piece minus this piece, if you do, so jump is going to be coming out to be 2 pi I, right? So this is a jump. So this function is discontinuous, right? So you cannot find differentiability of this function. This function is not differentiable also. You got it? Not differentiable. So in general, this is not differentiable. In general, this is not continuous, and because of the fact that due to the jump of 2 pi I. But if you define this function only in this range, then your function is very well continuous and very well differentiable. If you define the function in this range, then function is going to be very well continuous and very well differentiable. But at the branch line, the function has just above the branch line and below the branch line, function has two different values, and function is not defined on the branch. Therefore, the difficulties is coming for this logarithmic z. So it is not continuous or differentiable in general in another way. So you see, logarithmic function is not defined at the branch. So what is the branch point of the log z? So logarithmic z EFC is equal to 0. So branch point is z equal to 0. So z equal to 0 is the branch point. And if you see here this function, and then in that case, what you have to do is, this is the branch line, right? And you can say that z equal to 0. Z equal to 0 means y is less than or equal to 0 is branch line, right? Now you can also define the branch line depending upon our need. Suppose you have this, right? Now you can also choose the branch here, This is also the branch line. So for this, what we are doing here is, if we are moving from, in this case, what we are doing is we are moving theta 0 to 0 to pi, right? 0 to pi, right? And if we are moving from here negative direction, so 0 to minus pi, right? So what we are doing is, in the principal branch is minus pi to pi, right? But we are defining, this function is defined on, you say, minus pi to pi. We are not touching the branch line, right, in this interval. Okay, so in this interval, if you're not touching the branch line and branch line is removed, then this logarithmic z is going to be defined continuous, and even differentiable as well. All right, if you are going to define in this branch, right, minus pi to pi for this is called principal branch, right? Principal branch. Okay, suppose if you want to define some other branch, right? So let's say if I'm going to define from here, to complete this direction, right? So I started with 0 and left over with 2 pi. Okay, so what had happened is 0 and 2 pi open, right? This function is defined, but this is not principal branch. This is not principal branch, right? Because we have declared that principal branch like this. This is also a gap of 2 pi. This is also a gap of 2 pi, but this is not a principal branch, right? So if I want to say this is going to be the imaginary real axis is going to be your branch, like all x greater than or equal to 0 is going to be the branch, right, branch line, then in that case you can say that you are supposed to change your branch cut. Otherwise, what will happen if you take in this domain for this figure? So what had happened is 0 is included here. 0 belongs to this set, right? And if you cross this line, right? Then what had happened is branch line where function has two different values and jump of 2 pi I. So it means that function is not continuous, right? So while defining the derivative of such functions, be very careful because of the fact that you should not cross the branch line or branch point for the given function, right? So you cannot choose this as a branch for the principal argument, right? Because principal argument includes 0. If I select this branch, then what happened is I have to include 0, and 0 is the branch line exactly coming on the branch, all right? So branch point and branch line should not be taken for the given function, right? Because function has two different values. Function is even jump discontinuous, not even continuous. So we have to be very careful. So if I'm trying to deal with the, let's say, imaginary axis branch, right? Then in that case, this principal branch is okay. Okay. If I want to say, no, I want to select this branch, right hand side, like real axis branch, then you have to revise your interval. So it is no longer be a principal branch, but it will be one of the branch which lies between 0 to 2 pi to deal with the function, right? Suppose if you want to take your principal branch like your branch like this, uh, negative axis, or you can say that imaginary axis. Can I take? Yes, you can take, because then in that case you have to define your branch like how you are going to move it, right? So you should not cross. So you can say that this till here you can say, and then from, you can start from here to here. So what is the value? This is pi by 2, right? So you can start from pi by 2, 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 and 5 pi by 2, right? What is the difference? 5 pi by 2 minus pi by 2, which is 4 pi by 2, which is equal to 2 pi, right? And each gap is 2 pi, you see, right? And we are removing the points on the line because it should not touch. So if you want to select the principal branch as negative, as imaginary axis, you can do so far, right? But you should revise your argument, because you see pi by 2 open to 5 pi by 2. If you run counterclockwise, then your branch is not going to be touch at all. So you can always use the imaginary axis, and you can always use the real axis, and function is well defined because you have revised your branch. This is not a principal branch, this is a one of the branch. Similarly, you can do for negative imaginary axis as well. You can also define this. In that case, you take care of how the argument is going to run, right? So I hope you have understood. Not even this, you can also define the branch. I can say the branch any along any axis, right? I can say like this, along any axis you can define. Let's say I want to define this is a branch line, right? And branch point is z equal to 0. So what had happened is you have to take care of this, running from this to running from this, depending upon where you start from theta and where you end from theta, because this branch line or branch cut will not cross the curve, right? or or because if, whenever you cross this, your function is not at all defined and is even having jump discontinuities. On branch line it is not defined, right? And before this branch line, function has different value. After this branch line, function has different value. As we have already seen, the jump has 2 pi I, right? So be very careful while defining logarithmic z. Logarithmic z is not defined for all, z, as we have discussed. Suppose if I want to see first fundamental theorem of calculus. So integral a to b any function fz dz. So we can always find a differentiable function f, right? Fb minus fa, where f dash is equal to my f, right? Assume for time being, if your f is, let's say I can say 1 by z type, for example, right? Okay, so in that case, if you see, fz is equal to 1 by z when z not equal to 0, right, in entire plane, then what had happened is, because this function is not defined at 0, so if I talk about the derivative, the immediate idea comes into our mind is that log of z, right? So but is really derivative exist? This is the question. So answer is no, not in general, because if you see here, the function has assume, this is your capital F, right? So this function has jump discontinuity, right? So it is not even continuous or not even differentiable. So you cannot find, this first fundamental theorem of calculus does not hold true for such derivative of the functions, right? So in that case, how do you deal with? So how do you deal with this derivative? So you can define this derivative over the principal branch. For example, if you have a, curve, let's say I want to evaluate this integral, right, of this curve. Let's say some curve is there. Okay, so now the question is, if you see the branch point z equal to 0 is the branch point, and then the imaginary axis is going to be your branch, right? If imaginary axis is your branch, then you cannot evaluate such curve, right? Because derivative of such function does not exist. You got any point or not? So first fundamental theorem cannot be applicable. So how do you deal such type of stuff? You can change your branch. You can change your branch to here, right? Because branch can be either x greater than or equal to 0 or y less than or equal to 0. Either side you can take. But if you take the branch on the right hand side, then this curve can be evaluated because function is well defined. So how do you select argument? So in that case, your argument will start from here and move like here and come back to here. So this is theta equal to 0 and theta equal to pi, 2 pi, right? So your theta equal to 0 to 2 pi, this function is well defined because it is not crossing the branch cut or branch line, right? So this is very, very important when we used to define. Suppose if my curve which I'm going to evaluate is on this direction, right? Then branch, this has no problem. This branch has no problem, right? Because curve is not crossing. So for such functions, we can evaluate on along this curve, we can evaluate because I have selected the branch point as well as the branch line is negative imaginary axis. In that case, how do you find the your domain for argument? So domain for argument will be this. So 0 to pi, and from down here you have to take 0 to, so we have to take minus pi, right? So argument will be minus pi to pi, right? So in this case, your curve is well defined because it is not crossing the branch or it is not touching the branch at all, right? So you can define such functions, right? In case if you have, let's say your function is like defining on, I want to define the branch on this line, you can very much define because you can take the count, your argument from pi by 2 to 5 pi by 2 because 5 pi by 2 minus pi by 2 will give you 2 pi, right? So this type of functions, logarithmic z is defined in every argument of 0 to 2 pi in the open interval, and function is well defined. It's not crossing the branch, it is not cutting the branch, and it is differentiable, having no jump discontinuities. So function is continuous, differentiability will exist. But for general theta, right, it's not going to be like, let's say theta lies between 0 to 4 pi. So answer is no, because you have to make one more round and definitely it will cut either of the branch. So this is very, very important. How do you define? Even you can define the branch at any line. At any line, this will be the branch, but you have to take care of how your theta is going to take place, right? From here to here. Okay, so this you have to take care of. So any direction you can define branch from the origin, right? This is a very, very important point you have to think of about the logarithmic functions. Okay, thank you very much. Please like and subscribe this video.